And our next speaker is Daniel Baczkowski from the University of Findlay. So please go ahead.
Well, thank you, and thank you to all the organizers too. So I'll be talking about some ideas of Irdish, Sierpinski, Riesel, and more. Um, first of all, a covering system, or often called a covering, is just a system of congruences, or a set of congruences that covers the integers. So here we have, let's look at all the moduli in this system. They're all, least common multiple is 12 of these moduli. So if we look at the first 12 positive integers, those that are 0 mod 2, let's cover those. Let's cover those that are 1 mod 3, 1 mod 4, and then how about 3 mod 6, and then all the integers that are 11 mod 12. Since the least common multiple is 12, or the least common multiple of all the moduli is 12, this pattern will repeat every 12 integers, so we have a covering of the integers. Now, there's maybe something a little more special about this particular covering, and that is that it's a distinct covering, meaning that all the moduli are distinct and greater than 1. Now, this idea is probably one of the crucial ideas for some of the problems that we'll see here in a moment. And one of the classical problems or questions in number theory about primes, are there infinitely many primes of the form a power of 2 minus 1? Euclid showed that n has to be prime, or must be prime. This is not sufficient. The first couple of these are prime, but when you get to 2 to the 11th minus 1, that's not prime. And today we know these as Mersenne primes. Okay, well, you can see, well, instead of taking a power of 2 minus 1, what about a power of 2 plus 1? Are there infinitely many primes of this form? Well, it turns out that the exponent itself has to be a power of 2, and Fermat conjectured that these are always prime. The first couple of these or the first several of these are prime. And Euler actually showed that 2 to the 32 plus 1 factors into this product of distinct primes. And today we know these as Fermat primes. So you can make a conjecture, maybe it's not true, and you get your name listed here. Okay, well, instead of minus 1 or plus 1, what if you just take some odd number k? So for each odd number k, are there infinitely many primes of this form? And in 1849, de Pognac conjectured for each odd number k, there's at least one prime of this form. I mean, we know there's Mersenne primes, we know there's Fermat primes. Maybe it seemed reasonable to say that no matter which odd number k you take, there would be primes of this form. Now, this is really where the early ideas of coverings came in. So we'll view this as a congruence and think of this, if that's a prime, then k has to be congruent to minus 2 to the n modulo that prime. And in 1950, so 100 years later, Irdish actually proved de Pognac's conjecture was false. And then about another decade later, Sierpinski noted the same calculations showed that k times 2 to the n plus 1 is composite for all positive integers n. So when we're talking about Fermat primes, we mentioned, was it the first 5 of those are prime, and then when you get to F5, it factors. We're going to call those 2 prime factors, those 2 primes, we'll call them P and Q. And then there's just a quick observation here to make. So for non-negative j, 2 to the 2 to the j would be congruent to minus 1 mod fj. And if you square both sides, you get this. So the idea is going to be that if you take n's that are 2 to the j mod 2 to the j plus 1, then 2 to the n is going to be congruent to 2 to the j, in other words, minus 1, times some power of this thing. In other words, some power of 1 or 1, so you get minus 1. So in other words, 2 to the n will be congruent to minus 1 mod fj if you take n's this way. So you see in the next table, I'll display here that the first several rows all use this fact. So in this table, each row is an implication. And if you look at all of the congruences involving n on the left-hand side, those all form a covering of the integers. That's a covering system, that the set of all those congruences involving n. And then each implication, at least in the first several rows here, we have that k's are 1 mod the fj. And remember, the power of 2 was -1. So we get k times the power of 2 plus 1 is 0 mod the fj. And it's true for f5, and p being a divisor of f5 here, the same fact would hold in this row. And the row that's actually different is the last row. If you take n's congruent to 0 mod 2 to the 6 and k is congruent to -1 mod q, then you get this k times 2 to the n plus 1 is divisible by q. So what's happening here is if you can take a k that satisfies all the congruences for k in the middle of the table, which you can in this case by using the Chinese remainder theorem, then for every one of those k's, you get that k times 2 to the n plus 1 is composite. This is what we call a Sierpinski number. So in general, and this is using, it's probably more easy to see the ideas along the lines of a Sierpinski number, but this is essentially the same proof that shows the result of Erdős that de Poniak's conjecture is false. So a Sierpinski number is an odd positive integer k, such that k times 2 to the n plus 1 is composite for all integers n. The smallest known is 78,557. There are infinitely many of these Sierpinski numbers. For example, every k in this congruence is a Sierpinski number. And we use coverings to prove that an integer is Sierpinski. Now, if you change the +1 here to -1, those are called Riesel numbers. So an odd positive integer k, such that k times 2 to the n minus 1 is composite for all positive integers n. The smallest known Riesel number is this 6-digit integer. And every k in this congruence is a Riesel number. We use coverings to prove that an integer is Riesel. There's maybe for the past decade or so, maybe 2 decades, there's been a search for the smallest known Riesel and smallest known Sierpinski. You can look up 17 or bust or other sites, but there's been a push to find the smallest of each of these. So if we shift gears now and look at some other classical sequences, maybe the Fibonacci numbers or the Lucas numbers, these are both degree 2 linear recurrence relations. But these are 2 we'll look at next. So Luca and Mejia Hewitt showed that there are infinitely many Sierpinski Fibonacci numbers, and there are infinitely many Riesel Fibonacci numbers. Now, some joint work with Fazaranti and Finch-Smith, we showed that there are infinitely many Sierpinski Lucas numbers, and there are infinitely many Riesel Lucas numbers. And I'll try to give you an idea of what's used there in the proofs of those results. So for the Riesel Lucas numbers, it turns out that if you take k's in this gigantic congruence, that Lk is a Riesel number and a Lucas number. And here's a table similar to that of the Sierpinski numbers. All of the congruences involving n on the left-hand side form a covering system. And if you check the LKs appropriately, then each row gives you this implication. So this is telling us that if you can find a k that satisfies all of the congruences involving Lk in the middle, then the Lk times 2 to the n minus 1s are going to be divisible by one of these primes on the right. Well, it turns out that the k that satisfies all of these, or I should say the congruence of k's, is that congruence at the top. And this is technically one of 16 residue classes, and that gives us the smallest of those 16 residue classes. Um, for the Sierpinski-Lukan numbers, it's similar. So this congruence of k's will give us that LK is a Sierpinski number and a Lukan number. Similar ideas used here. But again, the crux is really putting this together so that you can find k's that satisfy all of those congruences. So these are linear homogeneous recurrence relations. They're known to be periodic modulo a prime, but it's not the case that you get every residue class modulo a prime. So maybe another classical sequence, the triangular numbers. So here's some joint work with Eitner and Finch-Smith, and also the hexagonal numbers. What we showed was that each of these sequences, and then also infinitely many others, has infinitely many Sierpinski and Riesel numbers. So I'll give you an idea of maybe some of those results. So here, looking at the triangular Sierpinski numbers, again, on the left-hand side, all of those congruences involving n form a covering of the integers. And if you choose k's appropriately, then tk times 2 to the n plus 1 will always be divisible by one of those primes on the right-hand side. So again, using the Chinese remainder theorem and taking k's that satisfy all of the congruences in the center. So for these k's, tk times 2 to the n plus 1 will always be composite since it's divisible by one of these small primes and something else. Likewise, for the triangular Riesel numbers, here's the table. And here's the congruence that satisfies these. Now, maybe I was a little subtle and said it very quickly, but we found triangular Riesel Sierpinski numbers. In other words, all three. That's actually this table. If you look above the line, then all of the congruences involving n above the line, that forms a covering, and all the congruences below the line involving n also forms a covering. So if you're just focused above the line, then if you can find a k that satisfies all the congruences in the center, that will give you tks that are Sierpinski numbers. Likewise, if you look below the line and you find a k that satisfies all those congruences in the center, then that will give you tks that are Riesel numbers. But this was put together in a way that you find a k that satisfies all those congruences and above and below the line, then you get a tk that's both a Sierpinski and Riesel number. And it turns out that for every k in this congruence, tk will be a triangular Sierpinski Riesel number. If you also attach to that congruence at the top that k is 1 mod 2, then you get hexagonal numbers that are triangular and Sierpinski. That are Sierpinski and Riesel hexagonal numbers. And then some other joint work with Eitner. So we showed that there exists infinitely many triangular numbers tk, such that tk times 2 to the n plus 1, that's what shows up in the Sierpinski case. So not only are they composite, but they're divisible by two distinct prime divisors for every positive integer n. And we can show the same thing for the hexagonals in some other cases. So the kth s-gonal number is defined in this way. And if you take your lowercase s here to be 3 mod p for each prime in this set, then tk, that triangular number, will be congruent to sk, that s-gonal number, modulo the product of primes in that set. So by doing this, you can use a similar table and you can show that sk is going to be a Sierpinski number. So essentially, you can use the triangular number result and modify it to get a result for infinitely many s-gonal numbers that have the same property. The property that for infinitely many of these s-gonal numbers, we have infinitely many of them that are Sierpinski and Riesel numbers. So it's a lot going on. Let me give a quick recap here. So this is a recap of the sequences with infinitely many terms that are Sierpinski numbers on the left. So this Sierpinski Fibonacci, and then on the right, Sierpinski Riesel, and then Sierpinski-Lucas, Riesel-Lucas. It's unknown, so you can see in the middle, it's the question marks there. It's unknown if there are Fibonacci numbers that are both Sierpinski and Riesel, or I should say it's unknown if there are infinitely many of them that are both Sierpinski and Riesel. And likewise, the Lucas case is unknown. But we have proven that triangular, hexagonal, pentagonal, and infinitely many polygonal numbers, there are, for each of those, infinitely many that are Sierpinski and Riesel numbers. So I had a student that was interested in degree 3 linear recurrence relations, and they wanted to investigate the Fibonacci-Riesel possibilities. And we found Fibonacci-Riesel numbers. So here TK represents the Fibonacci numbers. It's just similar to Fibonacci, but it's a degree 3 linear recurrence relation. And the table is similar to before. If you notice on the left-hand side, all the congruences involving n form a covering of the integers. And if you can find a k that satisfies all the congruences in the middle, then you get each of these implications telling us that tk times your power of 2 minus 1 will always be divisible by one of these primes. And as long as tk is large enough, then it's divisible by something else as well. They get all these composite numbers. In other words, tk will be a Riesel number. Now, just to display, how do you find these k's that satisfy each of the congruences in the middle? First of all, you wanted tk to be odd because in the definition of a Riesel number, you're taking an odd integer. So this first A set here is just saying that what are the k's so that are such that tk is 1 mod 2. Well, those k's are 1 and 2 mod 4. Likewise, for the first row in the table, what are the k's that are such that tk is 2 mod 3? Those are going to be 3, 8, or 10 mod 13. So you find all of these A sets for each of the rows on the table, and also you want k such that tk is 1 mod 2. And then you find the intersection of all these, and you can come up with a result like this. So if k is 3,817 modulo this 163 number, then tk is a Fibonacci-Riesel number. And it turns out there's 216 other residues among those, the intersection of those A sets that you can choose. And the smallest one is this 3,817. So keeping with the theme of finding the smallest Sierpinski number or smallest Riesel number, we have the smallest Fibonacci-Riesel number here. Okay, so we have Fibonaccis that are Riesel, or infinitely many Fibonaccis that are Riesel. So this is joint work with Keener. We were able to show that these other sequences, the Padovan, van der Laan, and so on, there's infinitely many of these terms in each of the sequence that are Riesel, and likewise infinitely many that are Sierpinski. The Narayana-Cow sequence, that was actually proven first by Razone and Harrington. We did come up with a smaller value, and just keeping with the theme of finding the smallest term in that sequence that's Riesel, and smallest term in that sequence that's Sierpinski. But still unknown if there are any of these sequences have infinitely many terms that are both Sierpinski and Riesel numbers.
Thank you for calling CVS Pharmacy. Our pharmacy is currently closed, but our automated system is here to help you.
It sounds like the pharmacy's closed. So, I mean, let's shift gears one more time and the odd covering problem. So does there exist a covering of the integers whose moduli are all odd, distinct, and greater than 1? So this is a unresolved conjecture, or I should say an unresolved covering problem. It was a problem of Erdős. In some joint work with Blodgett, we showed that an analogous problem to that of this unresolved odd covering problem holds affirmatively in infinitely many quadratic integer rings. So to be precise, we showed there exist infinitely many quadratic integer rings possessing a covering system with distinct ideal moduli that have norms greater than or equal to 3. And all of our coverings were explicitly constructed. Now, Cohen and Selfridge showed that there exist infinitely many integers not of the form plus or minus a prime power plus or minus a prime power. Luca and Stanica showed that there exist infinitely many Fibonacci numbers that are not of the form of prime power plus a prime power, or the sum of two prime powers. With Fazzaranti and Finch, we showed something similar for the Lucas numbers. And then with Eitner, we showed that there exist infinitely many triangular numbers that are not of the form similar to what Cohen and Selfridge did, but for triangular numbers. So plus or minus the prime power, plus or minus prime power. And then not only that for the triangular numbers, but we have the same result for the S-gonal, for infinitely many S-gonal sequences. So there are infinitely many S-gonal sequences containing infinitely many terms, not of this form. So I suppose a quick recap. These sequences have infinitely many terms that cannot be written as the sum of two prime powers, the Fibonacci's, the Lucas, and then also infinitely many S-gonal sequences with this property. And then joint work with Keener, we showed the same thing holds for all of these classical sequences. Now, I suppose like in the remaining few minutes, I just wanted to give you an idea of how someone goes about showing this using coverings. So Keener and I came up with a general method. I'll sort of show you that general method and a proof for the, let's say, the Fibonacci case. So combine those two. The theorem is that there are infinitely many Fibonacci numbers, tk, that cannot be represented as the sum of two primes, two prime powers. So here P and Q are prime and A and B are non-negative integers. And this actually occurs for every K in this congruence. So here's a sketch of the proof. So suppose that TK can be written as 2 to the A plus Q to the B. And this is where Q is an odd prime and A and B are non-negative integers. What we're doing is we want TK to be odd. So if TK is odd, then one of the prime powers is power of 2. Also, we don't want TK to be even. We don't want to try to get involved with the Goldbach conjecture, or it's already an extremely difficult problem. So consider this table. This is just, let's say, any table in general. So on the left, we first want this property. We want the congruences involving n to form a covering. There's two other properties that we will need. And the second is that we want in each row that 2 to the modulus, the mi, is congruent to 1 modulo the prime. And then the third property we'd like is that there exists an integer k satisfying all of the above congruences involving tk. And also we want tk to be odd. Since these are linear homogeneous recurrence relations that we're dealing with, then it turns out that by finding that, you essentially have a congruence of k's that satisfy that. So if we go back up to the top, tk is 2 to the a plus q to the b. Now, that means that a has to fit into at least one of these congruences involving n, since we have a covering system. So the set of congruences involving n forms a covering, so a has to fit into at least one of those congruences. Let's say that a falls into row I. In other words, a is congruent to ai mod mi, and that's where this, we're in row I of that table above. Well, then tk has to be congruent to 2 to the ai, which is just the same as 2 to the a. And that's because the 2 to the mi is congruent to 1 mod pi. So this implies that pi divides the difference of tk and 2 to the a, in other words, q to the b. So we know that pi has to be, that prime has to be the prime q. So in general, Q has to be among this one of the primes in the table. So the P1 through PT. And then the idea is to write this TK, which is 2 to the A plus Q to the B, as a particular S unit equation known to have a finite number of solutions. So for sufficiently large K in that congruence, then TK cannot be written as the sum of two prime powers. And then you get the result above. So essentially you can get it from this table. So the congruences involving n here on the left form a covering. And we have the 2 to the mi's, or 2 to the modulus on the left is congruent to 1 mod each of the primes on the right. And there is a K that satisfies all of those congruences on the right. Or in this case, it turns out a congruence of K's, so infinitely many of them. And that congruence is at the top here, the 3,817 modulo that mess. But we'll stop here and thank you.
Oh, thank you very much. Are there any questions for our speaker? There are two questions in the chat if you want to check quickly.
Okay, let me pull that up. Oh, so are there infinitely many Sierpinski numbers of the form n factorial? I guess I haven't thought about that. It's an interesting question. And then the other question, all kinds of questions popping up here. Let's see.
So maybe Michael Felicetta's question you should answer in the chat, because we need to move on to our next speaker. So
Okay.
Ashita, if you can upload your slides, that would be great.
Yeah, hi Nathan. Will it be okay if I share the screen?
Absolutely.
Okay.
It's not only okay, it's obligatory. Oh, looks very good. We'll start in 2 minutes.
Sure.